Hello everyone, welcome to the series of common source amplifier with resistive load. So in last video, I explained this common source amplifier using PMOS, but without consideration of channel length modulation and body effect. In this video, I'm going to cover this common source amplifier for PMOS with these two effects also. So in last video, I have covered these points for the calculation of gain without consideration of CLM and body effect. So this was the gain. So this was the gain expression. This was the gain expression, and I simply applied here. In the next, in this video, I'm going to tell how this body effect going to affect this signal model or this small signal model, how it is going to be modified. So yes, so when it was PMOS, we simply considered that this body is going to be connected at some potential. This is the body. If it is connected to the ground and this source is also ground, then there is a no potential difference. VSB or BBS equal to 0. But if there is a potential difference between these two, means BB is not equal to BS, then can say there is a VBS not equal to 0. Then body effect is going to be considered. And this effect is going to be replicated by using some current source, current source, GMB times of VBS. This was the model in NMOS. And the CLM effect, when the lambda is not equal to 0, it is going to be replicated by R out, where this impedance R out is nothing but 1 upon lambda ID. So same thing is also applicable for here, PMOS. But in case of PMOS, what you're going to do, this we know that source is at higher potential, that's a VDD, it's a DC, and this is your input, and yeah, this is your drain. So in this case, your body should be connected to the highest potential. Okay, and whatever the potential of source is, it should be connected with this. This is the ideal thing. So your body should be equal to the source voltage, that is equal to your VDD. In that case, VSB, let me clear this thing again to you, VSB equal to 0. So here we are going to use this VSB. But for for NMOS, I used VBS. So just think, I'll clear you this thing while when I'll draw this small signal model. So if this VS is not equal to VB, then your VSB is going to be some amount, and it is going to be reflected by this current source, which is your GMB VSB. Okay, and again here the lambda is not equal to 0, then this effect is going to be replicated by using and R naught, that is equal to 1 upon lambda ID. So now come to the plot or a small signal model. So this is your source, which is grounded, AC grounded, and yeah, this is your gate, this is your source, and this is your drain. So this is a source or current source, which is nothing but GM BSG, BSG, where BSG nothing but voltage between source and gate. And one more thing, the R naught is going to be replicated by here, that is your due to this channel length modulation. And third is a current source that is equal to GMB. I'll mention it here. That is equal to GMB VSB. Okay, and after that, this drain is you're connected to this RD, and we are taking output from here, from this RD. Okay, so we can see here one thing, that I have written VSB in case of PMOS, but I was writing VBS in case of NMOS. It is similarly in case of NMOS, I was writing VGS, but in case of PMOS, I am writing VSG. So for on the other hand, for it is VBS, so it is your VSB. I'm simply using just in flipping the S and B positions, and because of this small signal. So in this small signal, if I introduce this body terminal also, so if the body is at some higher potential or it's unequal potential, if the body is at some higher potential, then this BSB, what is going to be? So BSB is going to be some, can say, a negative value. And if this body is at some lower potential than the source, if the body is somewhere around here, so then in that case, this VSB potential is going to be positive. It depends on the position of your body with respect to your source. So now I can write the expression of the small signal uh, current. So this IS, this is your IS, or can say ID, which is entering into this. So now this complete model, so I'm removing this body here. I'm now removing the body from this diagram so that you can see it clearly. So this body is removed. So this complete model is nothing but a MOSFET represented by small signal. This complete model is your MOSFET. This complete model is your MOSFET, and this RD is outside again. So this current ID is leaving this drain terminal, which is going to which is going through ID. So one equation that is fixed, V out equal to ID multiply RD. This is one equation. And second equation is your ID is equal to what GM VSG plus this potential is 0 and this potential is V out for this R naught. So it will be 0 minus V out by R out, and third current will be your GMV VSB. So this is your second equation. And last equation will come from this input. So yeah, gate is applied at the input, or input is applied at the gate. So third equation will come from here, and I will write here. Okay. So third equation is nothing but a KVL from this point to this point. So it is going to give you VSG equal to minus V in. If we put all the values here, so I think I can show you by putting it. So yeah, if I put ID here, then what will be here? V out equal to GM VSG plus GMB BSB minus V out by R naught. This is completely multiplied with your RD. It means I have put, so okay, this is your second equation, this is your third equation, this is your second, and this is your third equation. Okay. So this expression of fourth equation, I can say, is coming by putting your second equation into the first. And after that, we can replace your VSG with the, okay. Yeah. So after that, we can replace this VSG with the minus V in, and this BSB. So yes. So if this body is connected at some point, it will be shown in the question. Then you can write this BSB also. But in general, this VSG is replaced by minus V in. So we can find this voltage gain here. So I think this is enough for this video. How to draw the small signal for the PMOS if this GMB or can say body effect is considered and channel length modulation is considered. So in next video, I'll cover these all gain calculations without drawing the small signal. So that will be very important. So I think this is enough for this video. Thank you.